All right, so this is our first lesson of our second last unit. We're almost there. Look how far you guys have come. So the last two units are going to be, well, our second last unit, the one that we're doing now, is kind of like your introduction into calculus and vectors. So what you're going to notice over the course of this unit is that we get into this idea of something called a limit, and we talk about rates of change. And then our last unit is going to kind of combine some of our previous knowledge so that we can graph certain types of functions and get to know how to do transformations of certain functions and things like that. So we're kind of like consolidating some of the different functions that we've learned about in the course and learning how to graph those functions and things like that. The first little part of this unit is about what we call a rational equation. We've learned about simplifying rational equations in grade 11. Do you guys remember rational expressions in grade 11? And you kind of like factored everything and then like cross-canceled things out, all that kind of stuff. So we're going to kind of recap that a little bit, and then we will learn how to actually solve equations with rational expressions in them. So rational meaning fraction. Yeah, Jonathan?
Are you going to be using radians this unit, or go back into degree mode?
I mean, it doesn't matter because we're not dealing with sine, cosine, or tangent. So unless you actually press the sine, cosine, or tangent button on your calculator, that's only where it matters whether you're in degree mode or radian mode. If you're just working with regular numbers, it doesn't matter what mode you're in. Okay, so we're going to kind of do a recap of how we simplify and state restrictions. Can someone remind us what are restrictions when we talk about fractions with variables in the denominator? Liam?
Restrictions are things that make the denominator zero.
Okay, so we, pardon?
Never mind.
Okay, so we don't want the denominator of any fraction to be 0 because that is undefined. If I have 6 divided by 0, that's an expression that doesn't make sense because we would be asking ourselves what multiplied by 0 equals 6. That's not possible, right? So we want to restrict anything that could have a denominator of 0. What we usually do in order to make that happen is we will factor and common factor everything. Okay, two things that multiply to 2 and add to 3 would be 2 and 1. Okay, and then I think we have a difference of squares on the top here. So we get x plus 2, x minus 2. And now that I have all multiplication with my rational expressions on top and bottom, I can actually cancel full expressions out. One on the top with one on the bottom. That does not mean that that is not a restriction. It just means it produces a different graphical restriction when I actually look at the function on a graph itself. So what are our restrictions here for this function? -2 and -1. So in my domain, if I am asked to state the domain, I would essentially want to say, usually this is a little bit easier to do with not using interval notation, but I would say x can be all real numbers, except for we don't want x to equal -1 or -2. Okay, now these two restrictions actually create two very different elements on our graph. So I'd like to take a look at the graph here. I'll flip back over to that in a second. Let's just pull up Desmos here. So I'm going to graph the original function. I always want to graph the original function to check, just because I will not see the restrictions if I put in the simplified equation. So we will have 2x minus 8, and then on the bottom it was x squared plus 3x plus 2. Okay, so we said that we have restrictions on -1 and -2. What do you guys notice? This is -1 right here. What do you guys notice about the area where x is equal to -1? What do we have? Jonathan?
It's an asymptote.
It's an asymptote. Now, -2 is right about here. So if I slide up to this on our graph, it looks normal at -2, but you guys will see when we hover over -2, hopefully I can get it, it is undefined, okay? So essentially what this would look like is exactly what you see here. When we hover over this, it's kind of like a hollow, undefined point, and that just means that our equation at that particular x value is just undefined. It doesn't have a y value. So our graph kind of like goes right up to that and then hops over it and continues from there, okay? Now, why would one of these be an asymptote and one of these be an undefined point? Why does that happen? What's the difference between what happened with each of these in the equation? Liam?
Negative x minus 2 or x plus 2 got canceled out, and x plus 1 stayed in the denominator.
Right, so I can still see the x plus 1 in the denominator. This causes a vertical asymptote. But if my restriction gets canceled out along the way, okay, you see how these x plus 2's get canceled? That actually causes an undefined point on my graph. Okay. Now we're going to pull in a little bit of our previous knowledge here as well, because I have a cubic that I need to factor here. So I have a couple options for factoring a cubic. What should I always check first for a cubic? Remember our quick factoring methods from Unit 2.
Should the exponents be in order?
Yep, exponents should be in order. They are, so we're good to go on that front. Annika, can you grab the back door there? Okay, do I go right into testing factors of 1 in my polynomial? So what do I want to check first, specifically for 4-term cubics? Factoring by grouping, right? So I want to check grouping first. So I'm going to let this be group 1 and group 2. How do I know if factoring by grouping is possible? Yes, Unit 2.
Have something that they factor out.
I need to get 2 brackets. When I common factor from each of them, I need to get 2 brackets that are the same. So when I remove the -1 from the second part here, see how we get x minus 1 and x minus 1? This tells me that we can, in fact, factor by grouping. So we have x minus 1 and then x squared minus 1, and this is actually a difference of squares. So we can get x plus 1, x minus 1, and I'm just going to enter that into my numerator there. So I have 2 x minus 1's, so I can say x minus 1 squared. And I'm also going to factor, common factor, a 3. I'm seeing one more special thing that can be factored here. What can be factored?
Squares.
Hmm?
Difference of squares.
Not quite. It's not difference of squares. We already factored difference of squares here. Pardon? Difference of cubes. So this is a good review for us getting toward the end of the year and toward exam season. How do I factor a difference of cubes?
X minus 1 times x plus 1 times x minus 1 here.
Nope. It's going to be a linear times a quadratic.
Oh, yeah, the a plus b is squared.
So how do I know what signs go into these spots here? So,
Last one's always positive.
okay, so the last one is always positive. What does the S and the O? So the same sign as what we have here is in the first one. And opposite sign, which would be positive here. Now what do I enter into these spaces? Okay, so if this is a cubed and this is b cubed, what are a and b?
X
X and we just say 1. right? The cube roots of those things are what we enter into this first space. So we want a, b, and then I want a squared and b squared and ab in the middle. So we're going to do x squared and 1 squared is 1, and then I will have 1 times x inside here. Okay, this guy right here is always a non-factorable quadratic that does not have any roots. Okay, so not only is it non-factorable, but if I were to enter it into the quadratic formula, we would get a negative under the square root there, and I would not be able to find any roots of that quadratic. So here's what we've got now. So since we know that this guy actually has no roots, there should be no restrictions that I can't, that I'm not able to enter in for x here. However, I do have restrictions here, but it will cancel out. So we know that that's going to be not a vertical asymptote, but an undefined point if it gets canceled out along the way. Okay, so this is where x cannot equal positive 1. Meaning that my domain is essentially, I can enter in any x that I want, it's all real numbers, except I want my x not to equal 1, because that is an undefined point. Oops, sorry. Okay, any questions on this one? Okay, so just as a little note to yourself, just in case you're looking back here, this guy always has no roots when you factor a sum or a difference of cubes. Okay, so no roots for that particular expression means also no restrictions for that expression if it's in a denominator. So far, so good? Okay, can I scroll? All right, so we're going to look at solving rational equations, which means these are actually slightly different from what we just worked with. This is a rational expression. Why is this a rational equation? What's different?
Has things on both sides of the equal sign.
Yeah, it actually has an equal sign. So an equation has an equal sign, right? It's something equals something. So if I know what the expression is equal to, I should actually be able to solve for that expression. So we're going to solve equations, and we're also going to solve inequalities. So things with like greater thans or less thans and stuff like that. So my suggestion would be that if we have like a rational equation equals a regular equation, or rational equation equals rational equation, find a common denominator if needed. So this one's already under one denominator. Make sure you state restrictions, and then we will actually kind of like cross multiply our equations here and solve. So I'm going to multiply up. Or I guess actually we can think about it as over 1. So if I cross multiply here, I should get x, or 6 times 1 equals x minus 1 times x minus 2, keeping in mind that x cannot equal 2 here. And then in order to solve an equation where I have a quadratic on one side, I actually need it set equal to 0. So what I'm going to have to do is actually FOIL out the expression on the right here and bring the 6 over so it's set equal to 0. Then we can potentially either factor or use quadratic formula to solve for what x is. So we're going to expand out here. I'll get x times x, negative 2 times x, negative 1 times x, and negative 1 times negative 2. I'm going to bring the 6 over, and we will get negative 4. And we're looking for two things that multiply to negative 4 and add to negative 3. If we can't find something, we'll use quadratic formula. Jonathan?
Negative 4 and 1.
Negative 1 and 1?
Negative 4 and 1.
Oh, okay. So negative 4 and positive 1 should work for us. I can do quick factoring because a is equal to 1 in this quadratic. So we have x minus 4, x plus 1. Meaning my x's are equal to 4 and negative 1. Seeing as x cannot equal 2 here, do either of those ones cause any issues with our restriction that we previously stated? No, they don't. So I should be good to go with both of these answers. And then I can actually check my answer here. We're going to check both of them. I want to check that when x equals 4 in my equation, that left side equals right side. And then I also want to check when x equals 1 or negative 1, that left side equals right side. So here I have 6 divided by 2 equals 3. And we have left side equals right side, so we're good to go with that. And then we have 6 divided by negative 2 or negative 3 equals negative 2. And I get left side equals right side. So these solutions must be correct. Okay, so you guys can always know whether your answers are correct or not by just subbing them back into your equation to double check. Any questions so far? We're good? Okay, can I scroll? All right, so there's your equation. Now we're going to take a look at an inequality. So inequalities are a little bit different because I'm looking specifically for where this function is greater than or less than or greater than or equal to or less than or equal to. One thing that we need to make sure of is that we do not cross multiply. Okay, you can do that when you have an equal sign in between, but not when you have an inequality in between. So we still do want this set equal to 0, but if it's not equal to 0, I will want to take whatever I have on the one side and actually just move it over to the other side. So if I have less than 1, for instance, I will move that over to the other side and it will be my expression subtract 1. So we'll kind of approach that in our next example here. But for now, we have less than 0, so we have an expression that's less than 0. I want to know for what range of x's this expression has y's that are less than 0. So we're going to just start by factoring our rational expression as we usually do. This is going to allow us to find important areas of our rational expression. So two things that multiply to 5 and add to 6. Alexandra? Multiplies to 5. 5 and 1, yes, that should work. Very good. And this guy here, this is a more complex quadratic. So I want to be able to factor. So I'm going to use my little splitting method that I kind of taught you guys at the beginning of the year. I want, when I split up 3, I want what I place here to add to negative 7 when I multiply across like this. So I think we're going to need negatives, a combination of negatives. And I can either do negative 3 and negative 1 here and here, or I can do negative 1 and negative 3. Now when I multiply across here, I get negative 2x and negative 3x. That doesn't add to negative 7x. But if I were to put negative 3 and negative 1 here, if I multiply across, I get negative 6 and negative 1, which adds to negative 7. So my combination is 2x minus 1 and x minus 3. Okay? You can factor this however you feel comfortable factoring. This is just my quick way of doing it. If you practice it, you'll get used to it. But I did post a factoring video for you guys a long time ago. So if you want to watch that and find a factoring method that works for you, you can do that. Okay, we are going to identify all restrictions and zeros. So the zeros come from the numerator. What are the zeros of the numerator? Or what are my solutions in the numerator here? They're kind of like restrictions, but I get them from the numerator, and this is where what x's I could input into this numerator to cause the numerator to equal 0, or to have a y value of 0. So what do I get from each of these brackets for my x's? Yes. These are my x-intercepts of my function, the zeros that we get from the numerator. The restrictions are from the denominator. What are our restrictions here? Jonathan?
1/2 3.
Positive half and positive 3. Awesome. Okay, so I taught you guys a little method back when we were doing polynomial inequalities. I think it was either end of Unit 1 or end of Unit 2, when we were sketching our polynomials and then deciding on which areas are positive and which areas are negative. I also showed you guys, rather than doing a sketch, we talked about a table. So we're actually going to use what we call a sign chart. Not to be confused with sine from trig, S-I-N-E, not that one. So we're going to do a sign chart as in positive or negative sign. And here's what I want to do. Each piece of my function needs to be included over on the left-hand side here. So each bracket, 1, 2, 3, 4, those are all going to appear in my table over here. If I have any values like out front, like let's say I have a -3, I'm going to make sure I either include that in its own table or I include it in front of like the x plus 5 or something like that. But for now we have x plus 5, we have x plus 1, we have 2x minus 1, and we have x minus 3. And then I'm going to have a section for the overall sign of my function. Okay, on the top, if you guys remember, we will usually line up the zeros from lowest to highest, so thinking of this as negative infinity and thinking about the end of our chart as positive infinity, so think about a number line almost. Now, not only do I want to include the zeros, but I also want to include any restrictions, because where I have restrictions, I might have asymptotes that cause my graph to kind of change in between those. So those are also important areas of my function. So I have 4 x's that I want to put up here. Actually, maybe I'll do these in their colors here. So I have -5 and -1. Those are x-intercepts. And then I have half and I have 3. Those are restrictions. Anyone remember what we do next? How do we use this now? Right, so I want like a number in between like negative infinity and -5. Sure. I want a number between -5 and -1. -3 sounds good. I want a number between -1 and positive half.
0.
0, good job, you guys remembered. Something between half and 3? 1, sure. 3 to infinity?
Infinity.
5. No, infinity, I can't do that because that's not even, that's a concept, it's not a number. Still not a number. Okay, what am I using these green test values for?
You put them into the end for x.
Okay, so each of these needs to go into each of these. And all I want to do is just record whether I get a positive or negative answer when I input those into each component of my function. So when I put in -6 here, I get a negative. When I put in -6 here, I get a negative. When I put in -6 here, I get another negative. And wouldn't you know, if we put -6 into this last one, we get a negative. Okay, yes, because I'm multiplying up here, I multiply x plus 5 and x plus 1. So when I multiply negative and negative here, that becomes positive. And we also multiply 2x minus 1 and x minus 3 on the bottom. So that also becomes a positive. And when I do positive divided by positive, I get a positive. Okay, -3. When I plug it in here, we get positive, negative, negative, negative. So overall, our function is going to be negative, yes.
Wait, how is the first one positive?
Because -3 plus 5 is positive 2. Right, when I put it in here?
No, I mean,
Oh, this one?
sorry, yeah.
So what is the what are you doing over here? That's the question, right? I do x plus 5 times x plus 1. So when I do negative times negative, what do I get? And then I do 2x minus 1 times x minus 3. So when I do negative times negative here, what do I get? And then I'm doing positive divided by positive, which gives me positive, right? Okay. Subbing in 0 here, we get positive, positive, negative, negative. Overall, when I do positive times positive, I get positive. And then we do negative times negative, we get a positive. And then we do a positive divided by a negative. So this divided by this, we get a positive. Okay, input 1, we get positive, 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 negative. Overall, what would this make my function if I multiply the first two, multiply the second two, and divide them? Negative. And the last one, we're inputting 5. We get positive, 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 positive. So overall, my function must be positive. And we are looking for where this function is just less than 0. Now, part of the important part of distinguishing between zeros and restrictions are that if I had less than or equal to 0, I would want to make sure I include the zeros but not the restrictions in my intervals. But I have just less than 0, so I don't really need to worry about using any square brackets at all. I want to exclude any zeros and I want to exclude any restrictions. But they are boundaries on my function. So I need to make sure I exclude these areas from my function. And I want to only include the areas that are negative or less than 0. So here's my interval. This is the first one, and this is the second one. So the answer will be between -5 and -1 in union with half to +3. Round brackets on everything because I don't want to include restrictions in the set because my function's undefined for those values, and I also don't want to include zeros because I'm only looking for where this function is less than 0, not less than or equal to 0. Okay, so remember, we're using the zeros and the restrictions as the boundaries of our function. We only use these test values to test in the function to see if those areas between are positive or negative areas. So far, so good? You guys remember this a little bit?
Yeah.
Yeah? Okay. May I scroll?
Yeah. We did that last year or this year?
We did it this year, beginning of the year. All right, so like I said, when we have a value over here, we still need it equal to 0 on one side, but I can't do the cross multiplication thing that I do when I actually have something equals something. So what we have to do is we have to move this term over. And similar to when we have an equal sign, when I move that +2 over to the other side of the inequality, it's going to become -2. And what I need to do here is I need to create a common denominator. So before I do that, I'm actually just going to factor and common factor what I have. Actually, you know what? I'm not going to do that. We're going to create a common denominator here. So I need to multiply the top and bottom of this by x squared plus 4. And what we have here is now we have a common denominator where we have this expression. And I'm actually going to bring this 2 into the expression here. So it'll be 2x squared plus 8. Okay, I'm going to leave the brackets around this, however, because when I put these two fractions together, the negative will actually have to go into both of those terms. So we're going to have one line. Now, once we merge these into one fraction, and I'm just going to gather up the terms that are common. Okay, and now we have something that's kind of in the format of what we started with in our first example. So your goal is just to kind of get all the like terms together, find a common denominator, get that together, and then we'll go and do the exact same thing that we did above. So we need to factor and common factor. I do have a 4-term cubic here, so before we go and use like polynomial division and the theorems and all of that stuff, we'll check to see if we can factor by grouping potentially. So here I can take out an x squared. I'm left with x plus 4. And here I can take out a negative 2. I'm left with x plus 4. So can I factor by grouping?
Yeah.
Yes. And then we have x plus 4, x squared minus 2 over x squared plus 4. Now, x squared plus 4 is not factorable. Are there any two things that multiply to positive 4 and add to 0? No, right? But they need to multiply to 4, right? So 4 times 0 is 0. That doesn't fit. Okay, I also can't really technically factor this, but it actually does have 2 roots inside of it. So here, when we talk about zeros and restrictions, okay, as far as zeros go, I can have x equals negative 4. That comes from this bracket on top. Now, if I have x squared minus 2 equals 0, and we solve for where x squared equals 2, I'm actually going to get 2 x-intercepts from that, positive and negative square root of 2. Okay, we know when we're solving an expression and it has like an x squared in it, I have to consider both possible options, that root 2 is squared and also negative root 2 could be squared to give us positive 2. How about the restrictions? Will x squared plus 4 ever equal 0? Is there an x I can enter in to make x squared plus 4 equal to 0?
No, because when you square a number, it's just going to be positive anyway.
Okay, so there's actually no restrictions for this function. So I'm going to use my 3 x-intercepts in my sign chart. Okay, so let's set up the sign chart. Okay, I'm going to have 3 x-intercepts along here. And then the last part of this is just going to be positive infinity. And each part of your function needs to appear in here somewhere. So I'm going to have x plus 4, x squared minus 2, and then x squared plus 4 over here. Line your x-intercepts up from lowest to highest. So it'll be negative 4, negative square root 2, and positive square root 2. And just so we know, approximately, root 2 is equal to 1.414. So when I'm thinking about this, I want to think like negative 414 and positive 1.414. Okay, so let's just say maybe we'll do negative 5, negative 3. 0 is a good one for this one, and then maybe we'll do 3 here. Okay, let's sub in each of these into our equations and record positive or negative. So here, I'm going to plug this into each thing on the left-hand side. This gives me a negative. This one's going to give me a positive, because I'll have 25 minus 2. And this one will give me a positive. So when I do a negative times a positive on the top here, I get a negative. And then we divide it by a positive. So that gives me overall negative. Okay, and then negative 3, we get positive, positive, and a positive. So overall, that gives us positive for our graph. For 0, we will get positive, negative, and positive. So overall, we'll have a negative section of the graph there. And then positive, positive, and positive again. So we'll have a positive section of the graph. Okay, what are we trying to answer here? What does the question ask us? This is the question I'm trying to answer, right? So what am I answering from the chart? We're looking for where this function is what? Or equal to 0, right? Greater than or equal to 0. So that's positive sections, and I also want to include any x-intercepts in my set with square brackets. So here's a positive section right here, and here's another positive section. And one thing to just kind of look out for is if you happened to have restrictions up here, I can never include restrictions with a square bracket because it's undefined. So if you had a restriction up here, which in this case we don't, they're all zeros, but if you did have a restriction up there, it always has a round bracket on it. Don't include it in your set. So can somebody tell me our answer here? Set up our intervals. Jonathan?
Everything in square brackets, negative 4 to negative root 2, in union with root 2 to infinity.
But round bracket on infinity, right?
Oh yeah, true.
So in this case, I'm looking for where it is greater than 0, which would be positive, but also equal to 0. So I want to include my x-intercepts or my zeros in my set with square brackets. Okay, make yourself a little note. Restrictions will never be included in your set. Restrictions must always have round brackets, as well as positive and negative infinity. Okay, so only zeros could potentially have square brackets, and the only time that zeros will have square brackets on them is if we have a greater than or equal to 0 or a less than or equal to 0. If it's just a greater than 0 or a less than 0, everything will have round brackets.